Hey everyone, have you heard about this wild discovery from the Large Hadron Collider? It's about antimatter and something called hypernucleus.
Yeah, it's pretty incredible stuff.
So we thought we'd do a deep dive into this whole thing, try to understand just what they found and why it's such a big deal.
The Large Hadron Collider, or LHC as most people call it, is this massive underground facility where scientists are smashing atoms together at almost the speed of light.
Yeah, I try to imagine that and my brain just sort of melts.
It's mind-boggling for sure. The goal is to recreate conditions similar to those just after the Big Bang, and by doing that, they can study the fundamental building blocks of matter.
So this discovery is about something called antihyperhelium-4, which, to be honest, sounds a bit like something out of a sci-fi movie.
It's definitely got a cool factor to it.
We've got an article here from SciTech Daily and some other reports on this finding from the ALICE collaboration at the LHC.
Right.
Can you break down what this antihyperhelium-4 actually is?
Okay, so let's start with the basics. We all know that the nucleus of an atom is made up of protons and neutrons, right?
Right.
Well, antimatter is like the mirror image of regular matter. It has its own versions of those particles called antiprotons and antineutrons.
Okay, so that's antimatter, but what about this hyper part?
A hypernucleus is basically a regular nucleus with a special guest star. It contains a particle called a hyperon.
A hyperon.
And these hyperons contain something called a strange quark, which makes them a bit different from your average particle.
Okay, hold on. Strange quarks. This is getting interesting, but I think we need to back up a bit.
Sure.
What makes a strange quark so strange?
Think of quarks as the even tinier particles that make up protons and neutrons.
Okay.
They come in different types, what physicists call flavors, and one of those flavors is strange. Strange quarks just have this unique set of properties that make them really interesting to physicists.
So these strange quarks are part of what makes hypernuclei so special, and in this case, antihyperhelium-4.
Exactly, and the really cool part is how they found it. They're smashing these heavy ions together at incredible speeds, creating conditions like those that existed just after the Big Bang, and it's in this super hot and dense environment that these rare particles can briefly appear.
They're basically recreating the Big Bang just to catch a glimpse of these particles. That's incredible.
Yeah, it's pretty amazing.
But how do they even find something that exists for such a short time?
That's where they're using some really high-tech tools. The ALICE team is using artificial intelligence, specifically machine learning, to analyze the massive amounts of data generated from these collisions.
So they're using AI to sift through all that data.
Yeah, it's like having a superpowered detective looking for clues.
That's amazing. So they found this antihyperhelium-4. How does this support the statistical hadronization model?
It's like this. You see, the model predicts how particles form in these extreme environments like the early universe or the LHC. And the fact that they found this antihyperhelium-4 in the amounts predicted by the model, well, that's a pretty big confirmation. It means our understanding of how these particles form is likely on the right track.
Wow. So it's like they had a theory and then smashed some atoms together at nearly the speed of light, and bam, it confirmed what they thought.
That's a good way to put it. But it gets even more interesting because this discovery could help us tackle one of the biggest mysteries in physics, the matter-antimatter asymmetry problem.
Now you got my attention. What is the matter-antimatter asymmetry problem?
Well, it's one of the biggest questions in cosmology. We believe that the Big Bang should have created equal amounts of matter and antimatter.
Makes sense.
But if that's true, they should have annihilated each other, leaving nothing but energy.
Yeah.
Yet here we are in a universe made almost entirely of matter.
So where did all the antimatter go? That's what they're trying to figure out.
Exactly. And this discovery of antihyperhelium-4, along with future research on how it forms and decays, could give us some answers as to why the universe looks the way it does.
Okay, so by studying this antihyperhelium-4, they might actually get closer to understanding where all the antimatter went.
That's the one idea that's really popular right now is CP symmetry violation. It's kind of complex, but basically it suggests that the laws of physics might be slightly imbalanced when it comes to matter and antimatter.
So maybe they're not perfect mirror images after all.
Exactly. There might be a tiny imperfection in that reflection that favors the creation of matter over antimatter. And by studying particles like antihyperhelium-4, we might just find evidence of this.
You know, this reminds me of a comment we saw in one of the articles about this discovery.
Oh, yeah.
Someone was talking about topological vortex gravitational fields. I have no idea what that even means.
Yeah, some of those comments can get pretty out there.
It's always cool to see people thinking outside the box.
Yeah.
But I think for this deep dive, we'll stick to the science coming from the ALICE collaboration.
Right.
So speaking of sticking to the science, I have a question about the practical side of all this. I mean, creating antimatter in a lab, it's like something out of Star Trek. Are there any real-world applications for this discovery?
That's a great question, and it's one that comes up all the time with fundamental research. It's hard to say right now what specific technologies might come out of this particular discovery, but history tells us that these kinds of breakthroughs often lead to innovations we never expected.
It's like how understanding electricity led to everything from light bulbs to the internet. It's hard to predict what these things will lead to.
Exactly. And who knows, maybe one day this research will lead to new forms of energy or even propulsion systems that we can't even imagine yet.
Antimatter spacecraft. That would be something.
It would.
But for now, it sounds like we're still in the early stages of understanding antimatter. So what are the next steps for the ALICE team? What more do they want to learn about this antihyperhelium-4?
Oh, there's still so much to explore. They want to study its properties in even greater detail, how long it exists, how it decays, how it interacts with other particles. All of that will give us a much deeper understanding of the forces at play within these exotic forms of matter.
I can't even imagine how difficult it is to study something that exists for such a short amount of time. It's like trying to examine a dream right after you wake up.
That's a great analogy, but the good news is the technology they use at the LHC is incredibly sophisticated. They're constantly improving it to capture more and more data about these particles.
It's mind-boggling to think about the level of technology involved in all this.
It's truly cutting edge. But, there's another really fascinating aspect to this research that we haven't even touched on yet. The potential role of hypernuclei in neutron stars.
Neutron stars?
Yeah.
Those are the incredibly dense remnants of collapsed stars, right? What do hypernuclei have to do with them?
Well, think about the conditions inside a neutron star. They're some of the most extreme environments in the universe. Extremely dense, incredibly hot, and under immense gravitational forces. Some scientists believe that under those conditions, hyperons, those particles with the strange quarks, could actually exist stably.
So instead of just popping up for a tiny fraction of a second, they could be a permanent part of these stars.
That's what some scientists think. And if it's true, it means that these hypernuclei that we're studying here on Earth could play a significant role in how these incredible objects behave.
That's a pretty amazing connection. The tiniest particles impacting the largest objects in the universe.
It really highlights the interconnectedness of everything in the cosmos. What we learn about the smallest bits of matter can have huge implications for our understanding of the largest structures out there.
It really puts things into perspective, doesn't it? Like, what we're doing here on Earth could help us understand these massive objects light years away.
Yeah, it's pretty mind-blowing.
All this talk about antimatter, it keeps making me think about the Big Bang, the very beginning of everything.
Right.
I mean, is it possible that by learning more about antimatter, we could get a clearer picture of how the universe started?
That's a big question, but it's definitely something scientists are thinking about. If we could understand antimatter even better, it's conceivable that we could unlock some new clues about those first moments of the universe.
It really makes you wonder what else is out there waiting to be discovered. If we can create antimatter in a lab, even for a fraction of a second, it opens up so many possibilities.
It does.
Could we actually use antimatter in some practical way? Like, what's the potential there?
Well, like we talked about earlier, antimatter has the potential to be this incredibly powerful energy source. If we could figure out how to create and contain it safely, it could revolutionize a lot of things.
It almost sounds too good to be true. Antimatter-powered spacecraft. New ways to generate energy. It's like something straight out of science fiction.
It does sound that way, but the potential is definitely there.
But I have to ask, what are the challenges? I mean, if antimatter and matter touch, they annihilate each other in a huge burst of energy. How could we ever contain something like that?
Yeah, that's the biggest hurdle. Containing antimatter is a huge challenge, and scientists are working on some pretty complex solutions. Things like magnetic traps and other advanced techniques to keep antimatter isolated.
So it sounds like we're not going to have antimatter spaceships anytime soon.
Probably not tomorrow, but who knows what the future holds.
That's what makes it so exciting. We're constantly pushing the boundaries of what we know and what we thought was possible. This discovery with antihyperhelium-4, it's just one step, but it's a step that takes us in a whole new direction.
Exactly. And it reminds us that we've only just scratched the surface of what's out there. There are so many more discoveries waiting to be made.
And maybe one of our listeners will be the one to make that next big breakthrough. You never know.
It's true. We're all part of this journey of discovery.
And that's what makes it so incredible. So to everyone listening out there, keep looking up, keep asking questions, and keep exploring. We're all in this together.
Keep diving deep.
And that's why we love doing what we do. Thanks for joining us for this deep dive, and we'll see you next time.